Recording is rolling. It is Tuesday, October 1st. I have this warm-up question for you guys. You guys remember yesterday you were doing this lab with like this classic Atwood. Suppose it's 2 kilograms versus 3 kilograms. What's the acceleration of the system? What's the tension and the string? Then we're going to be solving some chapter puzzles. So here's what I got for you guys. We solved a bunch of these first of all, law of inertia puzzles the other day. We'll maybe knock out a couple more of these. Then we're going to switch over to the second law of motion, start solving these. It's just here. Here's how we do this. Whatever ones we do in class, I'll just pick these up from you guys eventually, and then that's what I'll check off. So as long as you do the same ones we did in class, then I'll give you credit for those. All right. I did finish writing your guys' course quiz last night. I'll get that to you guys by the end of class Thursday. And then let's have this all due on Monday. All right, so yeah, whatever puzzles we do off that page in class, I'll check off and give credit for, and also you guys' quiz. So it'll all be there. All right, so back to this classic Atwood sort of question. So 2 kilograms, 3 kilograms. What is the, you say the acceleration of the system. Sometimes you see it phrased that way. Sometimes you see it phrased, what's the downward acceleration of the large block? Or what's the upward acceleration of the small block? All those questions have, of course, the same answer. They're all accelerating the thing. Right? And the follow-up question, hey, I wonder what is the tension in that string? Right? Give you guys a minute to solve that. At least solve for acceleration. Bet you guys can figure out that much probably. Here, if you guys need some paper, there's some paper out there.
Oh, thank you. Best. All right. Okay, here. Yeah, you can call gravity field 10 meters per second squared. Good call. Here, I'll start walking you guys through this here. No, don't start. All right, so there's a couple of ways to approach this one. Hey, you guys remember this poster from yesterday? It's classic Atwood poster. Okay, so this was your guys' lab yesterday. You guys were doing this, got your body diagram set up. Okay, so let's look at the whole thing. Ah, got it. 2 meters per second squared. All right, winner. Now the other day, back on Friday, you guys did this version of the lab, and I walked you guys through the solution. So you kind of look at these side by side and see, hey, what's similar and what's different. Okay? So here, tension in the string is the other question. Yeah. Right. So these both start out just really generically the same as with Newton's second law of motion. Isn't this pink box Newton's second law of motion? Right? Now, one way to get acceleration, what I tend to do in class is what's called a whole system approach. So I look at, say, the two boxes, one giant system tied together. And actually, from Newton's second law of motion, it leads straight to the answer acceleration this way. Right? So with the modified Atwood, the hanging weight was the net force. There were other forces, but they were either internal or they canceled. So the hanging weight was the net force. And it was driving both masses. Now with the classic Atwood, aren't these two forces competing? So I want to subtract those to get the net force. Again, this is from a whole system point of view. Right? That net force is acting on this total mass, and that'll give you the acceleration. Right? You got it. Yeah. All right. Yeah. Jake got both of those. So the acceleration is said 2 meters per second squared, and the tension was 24 newtons. All right, nice. Yeah. All right, so back to here. How could you get the tension? Now, to get the tension, you want to focus on either this block or this block in isolation. There's, I guess, a similar story for the modified Atwood, we're thinking the same thing. These two green equations down here, right? But for the classic Atwood double elevator looking one. Right, so from the point of view of M1, it looks like there's a tension force up and a weight down. That's the net force just on this block one. So this is Newton's second law of motion. Net force equals mass times acceleration, but only for block one. Right? From the perspective of block two, maybe if down is positive, got this weight down, the tension up is the net force driving mass two to accelerate. Okay? Now, it's the same acceleration for both, which is whatever you can get from the whole system's point of view. And it also works out to be the same tension. Let's try this with numbers. I'll see if I can get exactly what Jake got. The same thing. All right, and you guys ready to write this in your notes? All right. So here we go. I've got a pulley attached to the ceiling, maybe. All right. Gotta throw a string over and a couple of weights. So I got 3 kilograms right here. I got 2 kilograms right here. Oh, yeah. No, here. I wonder if it looks kind of like one of yours. You said 62. Oh, no, this is not off that page. Yeah, this is just extra. Yeah. Okay, it's kind of follow up from your lab yesterday. Because your lab yesterday looks like this. All right, let's get some forces. Guys, how much does 3 kilograms weigh?
300 grams.
How many newtons weight?
330.
30 newtons, right? Weight is mass times gravity field. Let's call that 30 newtons weight, right? Because that's 30 newtons. How much does 2 kilograms weigh? 20 newtons. If I draw this to scale, should this be about 2/3 as long?
Yeah.
20 newtons. Like you guys see that's short and that's long by a factor of 2 to 3, because 20 to 30 newtons, right?
What is the
Huh?
at the bottom?
Right. Yeah, it's gonna move that way. Zoop. It's gonna accelerate. Zoop, just like that. Yeah, maybe I start it this way. Zip. Right, no, because those are the external forces that I care about driving the system. I could actually solve acceleration just from that. But let's add on a little bit more to the story. So I think there's some tension in the string. Okay. Now, is the tension pulling back on the 3 kilograms and also pulling up on the 2 kilograms? I guess it's pulling up on both of them, really, right? Right. Do you guys think that the net force on the 3 kilogram guy is overall downward and the net force on 2 kilograms is overall upward? One's going down, one's going up.
Yep.
Right. So what I'm trying to set up is how large should this tension force be compared to 20, 30 newtons? You guys think the tension force has to be more than 20 newtons so it drives the small guy up, but also less than 30 newtons so that the large mass can fall down? Right? And it should be the same tension everywhere on the string. So if I draw that all correctly, try to hit all those details, maybe it looks approximately like this, pretty close. I think it's pretty close to scale, right? And we don't know what the tension force is yet, or well, I guess Jake does, but we're getting, you know what the tension force is. You solve that, which is really good, right? Right. But if I draw it correctly to scale, it's the same tension force. That tension force is more than 20 newtons and less than 30 newtons. Okay, great. So somewhere there. All right. So let's figure this out. I'll have acceleration is net force on total mass. That's Newton's second law. Newton's second law of motion. Newton's second law of motion, right there. So the acceleration. Now this is again from a whole system's perspective. Here's my 2 external forces that are pulling clockwise versus counterclockwise. So 30 newtons and 20 newtons, and they're subtracting from each other. You guys remember yesterday? If you put the same weight on both sides, what did it do? Yeah, stayed still. Because anything minus itself would just zero out. There'd be no acceleration. Yeah. And then mass total, could that be 3 kilograms plus the 2 kilograms? Just like that. Boom, boom. Right. So that looks like, exactly 10 newtons on 5 kilograms. Right. 2 meters per second squared. All right. All good. 2 meters per second squared. Okay. Now, when you get an answer in physics, usually a good idea to, no, this is just a starting question. Yeah, just to, and help debrief the lab yesterday too a little bit, because yesterday lab, yeah. All right. Usually get a bit to stand back and say, does this make sense in context? Right. Hey guys, what is the, you guys just told me this could possibly be 0 meters per second squared if they were the same weight. That's like a boundary condition. So, but if they're uneven weight, it has to be more than 0 meters per second squared. Right. Hey guys, what's the maximum possible acceleration for the setup? How about this? How about this? What if you take all the weight and put it on one side and just have an empty string on the other side? Huh? More? 10 meters per second squared. Right? Guys, if you put all the weight on one side and have an empty string on the other side, doesn't the weight just pure free fall? Ah, and look at that. The acceleration, yeah, that's somewhere between those two boundary conditions. I think that makes sense. I think it checks out. What do you think?
Yeah.
Okay. Now the follow-up question is, what is the tension in the string? And I'm going to split my paper and do this from two perspectives. Point of view, the 2 kilogram block. I'll do point of view, 3 kilogram block. Okay, so just that block or just that block. Here's what I'm moving on to on the poster. I'm moving down to these green equations right here. Here could be the 2 kilogram block. Here could be the 3 kilogram block. Right, guys ready to do that? Right. So from the point of view of the 2 kilogram block, I'm using my framework, net force equals mass times acceleration. Okay. Guys, the net force, could that be the tension pulling up minus the weight down? So tension force up, solid for, minus the weight down, results in a 2 kilogram block, 2 kilograms, accelerating at how much? How much does it accelerate? This right here?
Yeah.
Right there. We just solved that. 2 meters per second squared.
That's my physics.
2 and 2 is 4. Ah, all right. Guys, if this is 4 newtons, 2 and 2 is 4, and you add the 20 over, what does that tell you is the tension?
24.
24 newtons. That's right. 24 newtons. All right. What if instead you pick the other block, the 3 kilogram block? Let's try that out. It's the same framework. But now the net force is, you guys see 30 newtons down minus the tension force pulling up.
Yeah.
So let's call it down positive.
It'll be 36.
Huh?
It'll be 36.
Well, let's see. 30 newtons down minus the tension force up results in mass times acceleration. The mass is 2 kilograms again. The acceleration is still 2 meters per second squared.
Oh, I thought the mass is 3 kilograms.
Oh, whoops, sorry, you're right. Yeah, good call. 3 kilograms. There you go.
Yeah, 36.
Well, careful.
Wait, no.
Negative
Negative 36.
Wait a minute. What, guys, what's 6 minus 30?
Negative 24.
Negative 24 is equal to negative tension. Therefore, the positive tension is 24
What?
newtons. Ah, it's the same tension. Aha, ding. Because that one string, I bet, has that one tension in it. Is that true? Yeah, there you go. Okay, guess that? Okay. Now, to close this off, I mentioned too, the way we approach this is we went whole systems to get the acceleration, and then we focus on either one or the other block to get the tension. Of course, they get the same thing either way, right? If you take physics in college, then you might have a teacher or a textbook, one or the other, that actually starts with these 2 green boxes and does a system of equations. Now, if you do that, then you won't know the acceleration right away. So you have 2 unknowns, both the tension and the acceleration, and you can do probably some kind of substitution. You can solve it that way. Different way to go about it. All right. All right, you guys ready for today's puzzles? Puzzle time. Ready or not, here we go. All right, so I know the other day we solved a bunch of these first law. Yeah, I didn't realize until I printed these out. But tiny font, this looks like it looked like bigger font on my screen. So oops. I was trying to pick some good puzzles. Let's just do one more of these. Let's do number 64, Harry the Painter. You guys see Harry the Painter? And then we'll switch over to the next chapter. Harry the Painter, number 64. Swings year after year from his Bosun's chair. Look, he's painting because he's Harry the painter. His weight is 500 newtons. 64. His weight is 500 newtons, and unknown to him, the rope unknown to him has a breaking point of 300 newtons. Guys, if he just hangs the rope from the ceiling and starts climbing up it, is his rope gonna break? Yeah, it would. Why doesn't the rope break when he supports himself? The picture on the left, and then here, let's just read the whole thing. One day, Harry is painting near a flagpole, and for a change, he decides to tie the rope to the flagpole instead of like the picture shown on the left. Right? So we got two different setups. You guys see the picture on the left? He tied the rope over the pulley to himself, and on the right, he tied the rope over the pulley to this flagpole. Ooh, you guys see that? Okay. So what's the well, I guess the pure physics would be what's the tension in the rope in each case. So here we go. 64. Okay. Let's do 64 right here. We go. So let's draw. Here's Harry the painter on his bosun's chair. Let's do two setups. Right, we've got Harry the painter. Okay. And one setup, he's got the rope tied over to himself. And the other setup, well, there's like a flag. Okay. He's got the rope tied over a pulley to this flagpole. Okay. So A and B. Okay. All right, good so far? All right, let's do center of mass dot, center of mass dot. All right, let's do a free body diagram on Harry the painter. You guys ready? Free body diagram? Harry weighs, how much did I say he weighs? 500 newtons. Oh, guys, side question. What is the mass? What is his mass? In kilograms.
How many pounds is 500 newtons?
Okay, so yeah, 50 kilograms. All right, guys, take if you want to know how many pounds that is, take the mass in kilograms and multiply by 2.2. Get you pretty close. Hello, Mr. Griffin. And so back here, Harry Painter weighs 500 newtons. So he has a mass of 50 kilograms. Multiply that by 2.2. That's his weight in pounds. Okay, but we care about newtons. Okay. So, guys, what is approximately the tension in this rope? Tension equals what? Is that pretty close to 250 newtons? 250 newtons? You guys think? You guys see 250 newtons? Okay. All right, but over here, it has the same weight. Mg is still 500 newtons. Okay. Oh, guys, now what's the tension in the rope? 500 newtons. All right, you guys think? All right. So there you go. That'll answer that one. Right. Now, of course, if the rope has a breaking point of 300 newtons, you guys see where the rope is safe on the left, but it's going to break on the right? Do you guys see that? All right. All right. Next one. Here, let's go ahead and go to Newton's second law. So, because just the ones we've done in class, that's all the ones I'm going to check off on your when you have to finish these in, okay? Right. So as long as you've been doing the ones we've been doing in class, when I pick these up by Monday, then just the ones we've done in class is okay. All right. So Newton's second law of motion. Let's go ahead and start at the top and just start solving as many of these as we can get. Right. After day, of course, we got Wednesday, Thursday, Friday. I want to fit in at least one more day solving these puzzles and a couple other days for doing other things too. I consider a heavy crate resting on the bed of a flatbed truck. When the truck accelerates, the crate also accelerates and remains in place. Identify and discuss the force that accelerates the crate. Here, we'll just draw a free body diagram. That'll be good enough. All right, so call this chapter 5, we'll call it. Yeah, chapter 5, Newton's second law of motion. Alright, so 106. Alright, well, I don't know, I think it's supposed to be first law is law of inertia, second law is F equals ma, third law is equal and opposite. So these questions kind of correlate. Sometimes not exactly. That's all right. We'll just answer the questions one at a time. All right, so here could be a flatbed truck, something like this. Got some wheels on it. All right, it's not a very good truck. Whatever. We got a crate. It's going to draw a crate. Got a center of mass. Okay. Now the truck is, they said accelerating forward. So maybe it's like moving forward, speeding up. That's one way to accelerate forward. Right? You can move forward, speeding up. Right? And if that crate is at rest relative to the truck, it's just sitting in the flatbed, that means relative to the rest of the world, it's also accelerating forward. Let's get some forces on this crate. What's one force on the crate? Yeah, it's weight. So mg could be its weight. What force is holding it up?
No. Oh, I don't know.
The starts with an N. Normal force. Normal force. Okay. Okay. Now, if you want the crate to accelerate forward, do you think you need some forward acting force? And guys, what force is that that's acting forward? If it's on a flat surface, friction.
What?
Friction. That's it. There you go. All right, that's the free body diagram. 106. All right. Okay. And then, okay, so it's three individual forces. And is it the friction force the net force, which is also causing the acceleration? Okay. All right. So could say more about that, but let's go on. Let's go number 107. 107. What we got here? Zoom in. Three identical blocks are pulled as shown. Hey, look, it's the chain gang. Just turn sideways. Or did I tell you guys this could be like a train, like choo choo, like a train moving along, right? Maybe something like that. So we got here. It's showing a horizontal friction on the surface. The tension in the hand is 30 newtons. What would be the tension is in these blocks? Okay, notice it says they're identical. You see identical blocks, right? So you know they're all the same mass. So from the point of view of pulling the person pulling, there's some total mass. But from the point of view of this rope here, isn't it only pulling these two blocks, which is like 2/3 of the total mass? And then this rope is only pulling 1/3 of the total mass. You guys think? Something like that? All right, so let's do 107. Whoops. 107. There we go. In fact, I'm just gonna make up a mass because it turns out it doesn't matter what the mass is as long as they're all the same. So I'm just gonna make up something. Is it okay if I call them each 1 kilogram? Is that all right? Okay, I can call this guy 1 kg, 1 kg, 1 kg, 1 kilogram each. Is that all right? Okay. All right. So we've got this rope. We're pulling. All deal. Okay. You guys got that? All right. Let's get some forces. So I know this guy's pulling. Yeah, 30 newtons of force. I'll call it F pull equals 30 newtons. 30 newtons. Okay. All right, guys got that?
Yeah.
Okay. Okay. Now I know that there's a tension here and there's a tension here. Maybe you can kind of reason it out. But let's do some vertical forces just for completion here. Does each of these blocks have a weight and a normal force, you guys think? They're balancing out? I'm gonna do those real fast. So I just made up 1 kilogram, but let's just run with that. Aha. Mg could be 10 newtons. Normal force could be 10 newtons, like that. Mg, normal force. Mg, normal force. Boom, boom, boom. Okay. All right. So that's all side. Okay. All right. Oh. Now, guys, this 30 newtons, doesn't this have to pull how many total kilograms? 3 kilograms, right? Now, if there was no friction, that would be accelerating, wouldn't it? Right. And accelerating how much? 30 divided by 3 is 10 meters per second squared. That's like, oh, that's like 1 G, isn't it? Zoom. Right? It's pretty good. Right. Right. Now, here, I'm gonna think it's sort of backwards. Let's start from the caboose back here. You guys see the very last one? Right. Now, isn't true these all have the same acceleration. And you guys just told me it's 10 meters per second squared, because 30 divided by 1, 2, 3 kilograms, 30 newtons on 3, that's 10 meters per second squared. Okay. So guys, how much force does it take to accelerate 1 kilogram? It would be 10 newtons, wouldn't it? You guys, therefore, what is the tension in this rope? 10 newtons. 10 newtons. Right? Let's go. Tension equals 10 newtons. There's that tension, right? Is that true? Guys, if it's 10 newtons pulling this one to the right, is it the same tension pulling this one to the left? 10 newtons, is there one tension in that rope? That one's also 10 newtons. Tension equals 10 newtons. That'd also be true, right? But hang on a minute. Is this block? Yeah, 20. This is 20 newtons right here. How many newtons is this right here?
30.
20. Okay, so 20 and then 30. There you go. So guys, the tensions go, I got 10 newtons, 20 newtons, 30 newtons of tension. Okay, he's pulling with 30 newtons. You guys see as you go back, it gets successively less and less tension? Yeah. Okay. Guys, yeah. Okay. Do you guys remember when you did the vertical version of this? You guys remember holding 3 weights on spring scales? And the top spring scale was reading a lot of weight. And the middle spring scale was like a medium amount. And the bottom spring scale was reading the smallest amount of weight at all.
Your audio's loud now.
Yeah, that's what I got. Yeah. All right. You guys getting on 107? Let's see what's next. Next one. Here. Tell you what, this next one we'll just talk about a little bit. Guys, look up here. Pull a wagon. Across a lawn with constant velocity. You have to exert a steady force. Now, guys, constant velocity. Constant velocity means what's the net force for constant velocity? 0. So if you're applying a force, do you think there's also maybe a resistive force keeping that in check?
Yeah.
Possibly friction, maybe. Right? Discuss and reconcile the fact Newton's first law, which says that motion with constant velocity requires no force. Okay. Well, okay, because it's no net force. So actually, here, I'll go and draw this one out. Let's draw this one out. 108, right? 108. Let's draw this wagon. So you got like a big old Oregon Trail spokes of that. Center mascot. And let's get a velocity. Say there's a velocity going to the right, something like that. All right, here's the setup. Okay. So let's get some forces going. I bet this thing has a weight mg. I bet it has a normal force Fn. That's canceling that out. Okay. I bet you're pulling with some force F pull. But if that was it and you stop, it would be accelerating, which would not be constant velocity. So you need probably a friction force, I think. Okay. Something like that. Right. I think that could be it. That could be it. All right, number 109. 109. Yeah. Oh, yeah. That's it. That's the whole thing. That's 108 right there. That's the whole thing.
Wait, so what do we bring?
Yeah, you just draw that diagram.
What? You draw a little bomb?
Yeah.
Just like turn in our work with it.
Yeah. You can just just turn your work. Just show you. Yeah. Just write this. That's all right. Yeah, guys, on 108, just draw that free body diagram. That's good enough. All right, 109. A common adage, common saying goes, it's not the fall that hurts you, it's the sudden stop. Ooh, right, you guys ever heard that? Right, like you fall out of a 3-story window. While you're falling, you're probably okay, but like when you hit the ground below, that's when it hurts, right? Right. So what does that have to do with physics? Let's draw a free body diagram for this. This could be 109. So let's draw let's say you jump off a cliff, like you're halfway down here, and later on, Well, you kind of forgot. Oops. Yeah, you can draw a waterfall. Right? Let's say this is the point that he's crashing.
That's too graphic for this film. You can't be drawing that stuff.
Well, looks like we're doing a physics analysis. Hey, he's a stunt man. He's all right.
Oh, he's a stuntman. Okay.
Can't kill this guy. All right, so, guys, while he's in free fall, what does the free body diagram look like? Just one force, right? Just mg, right? Hey, maybe there's a tiny air drag, whatever. But I think that's the main force that matters. Right? Now, guys, while he's crashing, does he still have the same gravity pull from Earth?
No.
Okay, I think it's the same, right? Right. But there's definitely more going on. Now, here's Newton's second law of motion. Net force equals mass times acceleration. Okay. Now, net force. Do you think that the force I haven't drawn yet could be the normal force from the ground? You guys think? So the normal force minus his weight, that would be the net. Now I haven't drawn the normal force yet, but when I do, that would be a difference in forces, right? The normal force up minus his weight down. Okay. Equals mass times acceleration. Now, guys, his acceleration. It's like when it was in free fall, guys, when it was in free fall, what was his acceleration? Yeah, 10 meters per second squared, right? But when he's coming to a sudden stop, do you guys think, yeah, right, he's going to 0 meters per second from however fast his crash speed was. Isn't that, guys, what was the original definition, the original perspective on acceleration? Was it a rate change in velocity? Is that like change in velocity over a change in time?
Yeah.
Right? So change in velocity over change in time, right? So it's like this: normal force minus weight is equal to mass times. Now, if you're going to 0 from some crash speed, the difference would just be the crash speed. So v crash, which is like square root 2gh, and t, guys, this time of crashing, this time interval, is probably like a tiny fraction of a second. You guys think it might be like 0.1 seconds or something?
Yeah.
To go from really fast to not moving, right? Okay, so, huh? This is a multiply here. Yes. Okay. So, guys, for example, what if he was crashing at like 10 meters per second? I'm just thinking something up. Huh?
Is he okay?
Yeah, he's all right. He's all right.
How do you know that?
Because it.
What's the height of the slope or whatever?
How they oh, he's all right. Okay. Here, maybe it's a pool. He's got some water. He's got some water. He's all right. It's a water. I suppose he was his splash speed was like 10 meters per second, and that happens in 0.1 seconds. Guess what is 10 divided by 0.1?
And 1.
Give me 100.
What?
Right, here, guys, what is the change in 10 meters per second, all happening in 0.1 seconds? That'd be 100 meters per second squared, right? And then multiply by whatever's mass is, right? Here, guys, if this is 100 meters per second squared, and free fall gravity is only 10 meters per second squared, you guys see in my made up numbers, he's already, this is dwarfing this by a factor of 10.
Sure.
Right? So, guys, suppose he weighs like 100 newtons. This could be like 1,000 newtons over here. It's like 10 times as much.
Yeah.
Right? So that normal force is going to be 10 times as much, or 11 times as much. Here's the normal force. Whoosh. Right. Now that's only while he's crashing, and that only lasts for a tiny fraction of a second. Yeah, you can plug in different numbers, get different numerical answers, but it's going to look something like that. Okay. Right? Oh, there you go. So that's a huge net force at the moment that he's crashing. All right, so we're going a little bit. Number 110.
Yeah, bro.
Sketch the path of a ball tossed vertically into the air. Ignore air resistance. What, 109? Here, that's 109 right there.
We have to draw it out.
Yeah, or draw something or write something. So yeah, got that. Right. Yeah, guys, you guys see a lot of the questions out of this book are like, how do you How do you approach these questions? How do you think about them? You could plug in different numerical values. You could give him whatever mass. You could make the clip whatever height to get result in whatever crash speed. Right? But yeah, we're really like real big picture on these questions. Right, number 110. Sketch the path of a ball, toss vertically into the air, ignore air resistance. We'll do halfway to the top, at the top, halfway down. Draw a force vector in all three positions. Yeah, all right, let's go do that. We'll just draw 3 free body diagrams for 110. That's all we need for 110. So number 110. Right. Show you how to draw a little diagram first. So here's the ball. It's gonna go up. It's gonna come back down. All right. All right. So you guys see at some point it's going up. At some point it's coming back down. We'll call this scenario A, scenario B, and scenario C. All right, you guys got A, B, and C? All right, there we go. Let's do the diagram for A, the diagram for B, the diagram for C. Go ahead and draw a ball for each one of those. Center of mass, center of mass, center of mass. Okay. Remember, in frame A, it's moving upward. At frame B, it's at the top, and at frame C, it's moving downward. Thank you. All right, you guys got that? So moving up at the top and moving down. Okay. Now remember, we're ignoring air drag. Air drag is negligible. Not even going to consider it. All right, you guys ready? All right, so we got to draw the free body diagram for each one of these. So guys, while the ball is moving up, what forces are acting on it? Well, what's one force? Yeah, it's weight. Pull it down. I like mg. Right. Are there any other forces, or is that it? I think that's it. Right? So we're ignoring air drag. So I think that's it. What about the very top? What forces at the very top?
Wait.
Yeah, it's weight.
Oh, wait.
Is there anything else? Oh, how about coming back down? Got to wait. Anything else? Hey, are those exactly identical? Yeah, they sure are. Same free body diagram. So remember, free body diagram, you care about the forces. You don't care about the velocity so much. In this case, it doesn't even matter. Okay. Maybe if there was a block sliding across the floor, because it can tell you the direction of the friction force, which would be opposite of that. But other than that, yeah.
Mr. Griffin, when's the next lab?
Next lab?
Yeah.
There's 2 labs I want to fit in pretty soon. So I want to have you guys do some stuff with some spring scales and possibly create a Varanon frame.
What?
Yeah, so
Varanon frame?
maybe tomorrow, maybe. We'll see.
What is the Varanon frame?
Wait, I see.
That-
Okay, number 111. 111. As you leap upward, how does the force you exert on the ground compare with your weight? Ooh, as you leap upward, do you think you're overall accelerating upward during the jump?
Sure.
So there should be a net force, right? Should be a net force. So let's do 111, jump. Right, during the jump. Ground. Here's, how about a person, let's say, here, I'm gonna put him like in this squatting position. He's jumping. He's jumping. Whoa. Does this guy have a weight pulling down? mg. Right. Okay. Now guys, if he's pushing himself upward, so overall he's accelerating upward, how does the upward force compare to the downward force? He's accelerating upward. Be bigger, right? Be bigger. Okay. Oh, and what should I label that force? What kind of force is that? Normal force. That is.
It is that.
Force from the ground. Normal force. Fn.
Okay, you just said that. Well, that could be like.
All right. All right. 114, 115. It looks like these two go together. What is the net force acting on a 1 kilogram ball in free fall? And then The follow-up question, 115 says, what if there's 2 newtons of air resistance? So let's do these two. 114. We got a ball. 1 kilogram is the mass. Okay. What is the net force in free fall? So suppose you just drop it off the edge of a cliff. Does it have a weight? mg. And guys, what is that force equal to on Earth about? There you go. Pick your favorite, 9.8 or 10 newtons, because it's a weight, it's a force. 115. So same ball. Let's say it's been falling a while. Now it's facing some air drag. Has the same weight as before. mg is 10 newtons. That's the same. Okay. They said air drag is 2 newtons. Now, guys, if the ball's falling straight down, which way does the air drag point? Straight up. Force drag is 2 newtons. Okay. Therefore, the net force, F net, is how much? 8 newtons. Right? Let's go back. Here, I got my own question. What is the acceleration of the ball at that moment?
2,
More than 7.
Here.
1.
What does Newton's second law of motion say?
4, 5,
Oh, Jake.
6.
Net force on mass?
Yeah.
What's the net force?
So
8.
1. What?
So
Oh.
1/5
8 newtons.
or 4/5.
What's the mass?
4/5. 1.
8. Oh, so
1
8.
kilogram?
Oh.
Ah,
I said it.
yeah. All right. I think I missed it somewhere there.
It wasn't
8 meters per second squared.
He did 1, 2, 3, 4. Yeah,
No, guys, that's just true. That's just true at that moment, right? Right. So is the ball still speeding up?
Yes.
Yeah, it's accelerating. Now, as it speeds up, do you think that drag force is increasing? Right? Is it drag force proportional to v squared? Right. So this is only true for like 1 instant, and then it's gonna accelerate not as much. All right. What else we got? 120. Right here, a 400 kilogram bear is grasping a vertical tree, sliding down at constant velocity. What is the friction force that acts on the bear? Discuss how constant velocity is key to your answer. All right, let's do a free body diagram for the sliding bear. 120. All right. You guys draw a tree trunk. You guys draw a sliding bear.
Hey, is that that?
Why am I in our teacher?
What the fuck is that?
It's a bear. The guy that came out.
That looks like the Sherman Ulster salt.
What? Oh, Sherman Ultra.
All right. Let's say his weight was. Okay, we got his mass is 400 kilograms. 400 kilograms. Okay. All right, so what is this bear's weight equal to? About 4,000 newtons. You guys think 4,000 newtons? Okay. Hey guys, if he's sliding down at constant velocity, here, constant velocity means that the acceleration is equal to what?
It's very unrealistic, but there's only 88 pounds.
0. Well, maybe he's a baby bear. 0 meters per second squared. And if the acceleration is 0, what's the net force? 0 newtons. If the net force is 0 newtons, what is the friction force?
0.
Huh?
0.
No.
1.
10.
4,000
Oh.
newtons.
Hey, I was
You guys see that force and that force cancel out? so that the net force goes to 0. Right, guess that? All right, guessing that's a good pause point right there. Good pause point. There we go.
Slide and bear.